Hello, so in today's video, we're going to look at the idea of inverse functions. But before we do that, let's just get some motivation for this. So let's just think about this function here. This is a one-to-one function on the left-hand side here. And on the right-hand side here, I've drawn a many-to-one function. So we've gone through this in previous videos, what one-to-one functions are and what many-to-one functions are and what the difference is. So this first one's a one-to-one function. Now, let's just, out of interest, let's just reflect this graph in this mirror line here. So this is the line, the diagonal line, y equals x. So let's just reflect the graph in this line here. What do we get? I mean, we'll get something that probably looks something like that if we do that. Okay, so what do we notice? Well, this blue line is also a one-to-one function too. So this is one-to-one. Let me just make a note of this, that this function here is one-to-one. And this function here is also one-to-one function. So yeah, this blue line is also a function too because it's one-to-one, and that's an example of a function. Okay, so that's what happens if you reflect this graph. What happens if we reflect this graph here in the line y equals x? You should get a shape roughly like this, kind of like a quadratic, but on the side instead. So perhaps uh, something like that. Okay, so that's what you get when you do that. Now, is this a function? I mean, the first black one is a many-to-one function, so we just set up there. So this is many-to-one. Now, this function here, well, I shouldn't say a function. It's not a function because we've seen this before when we do the vertical line test. If we draw a straight line down a graph, if it has more than one point of intersection, it's not a function. And this is not a function. So this blue line here, this blue curve, is not a function because it's a mapping, and in fact, it's a it's a one to many mapping. So this is a one to many mapping. This is not a function, so not a function. Okay, so this is just a bit of motivation for what an inverse function is, because as we'll see on the next page, an inverse function is literally the function that you get when you reflect a function in the line y equals x. So that's what an inverse function is. So if this is y equals f of x, this black line here, reflect this in the line y equals x, you get this blue reflection line here, this curve here. This is your inverse function. And we call inverse functions f minus one. So that's the notation here. So the really important thing to note with this notation is that f minus one is not the same as f to the power of minus one. That's just something to be aware of. So similar to like how sin minus one on your calculator or cos minus one, tan minus one is the inverse function of sin, cos, and tan. That's what they are. They're the inverse function. So they are literally the reflection in the line y equals x. That's what an inverse function is. It's not to the power. This is not the function to the power minus one. This is an inverse function. It's the notation that we use. So it's just notation. Yeah, so as we say down here, so an inverse function is the function you obtain by reflecting the graph y equals f of x in the line y equals y equals x. So in other words, then f of x, f minus one x, the inverse function, is the function. There's a function you get when you swap the x and y values around. So it's a function you get when, let me write that a bit neater. So when you swap the x values, when you swap x values with the y values. So I'm just using this notation here to denote we're swapping x with y values. So essentially, when you reflect a graph in the line y equals x, you're flipping over the y-axis to your x-axis and vice versa. That's kind of how it works with these reflections. So yeah, that is what an inverse function is. So yeah, a key point to make, which I kind of was trying to allude to at the start of the video, is that one-to-one functions have inverses. So every one-to-one function, for example, like this one here, this is a one-to-one function. This first example back here, this is a one-to-one function. All one-to-one functions have inverses. They all have inverses. However, these many-to-one functions, like again, this example here, they don't have inverses. So I've written two examples here and here actually. So f of x equals x squared for a domain where x is bigger than zero. So that's kind of the quadratic graph when x is bigger than zero. Okay, so this is a one-to-one function because actually there's every y value has a unique x input. So this is a one-to-one function. We can do this this horizontal line test to show that. So this is a one-to-one function. And I mean, if we were to reflect this to get, let me just make a note here that this is f of x. That's f of x there. So reflect this in the line y equals x, perhaps something like this. You would get this new graph, this blue graph, and that's also a one-to-one function as well. So yeah, this is all fine basically. This is a function, and so an inverse function exists. So that's one-to-one function. So every one-to-one function has an inverse, and every inverse function is a one-to-one function. That's a key point as well that I'll make here. Every one-to-one function. Sorry, every inverse function is a one-to-one function. So every inverse. Sorry, let me write that again. Every inverse function is a one-to-one function. So that's a key point from this because, yeah, for every one-to-one function, there exists an inverse. So every inverse function is a one-to-one function. And this second bullet point I made here. So many-to-one functions do not have inverses. So again, this example here, f of x equals x squared. For x, every x in the real numbers. So every real number on the real number line. So something like this. Yeah, this doesn't have an inverse because even though this is a function here, this x squared graph, that every real number is a function. This here, this is a one-to-many mapping. This is not, so not function. So yeah, that there is no inverse function for many-to-one functions. Okay, so let's look at an example then. So let's say we've got f of x equals 3 minus 2x over x plus 4 in a domain where x does not equal 4. So x can be any real number. Let me just make a point about this. So x can be any real number, but apart from negative 4. Why have I specified that? Well, because actually if you sub in negative 4 into your denominator, you get minus 4 plus 4, which is 0. Dividing anything by 0, you can't do that in maths. That's undefined. Okay, let's go ahead and find the inverse function. So the key thing is you're just going to write y equals 3 minus 2x over x plus 4. So that's kind of, I guess, the graph of your f of x function. That's how you would, that's the equation of your curve. Now we need to, so again, the key thing with inverse functions, we're reflecting it in the line y equals x. So we're doing a transformation. We're changing the x coordinates with the y coordinates. We're swapping them around. That's what we're doing. So we're now going to do a transformation. We're going to transform the x coordinates to the y coordinates and the y coordinates to the x coordinates. So what we get if we do this is we get x equals 3 minus 2y over y plus 4. Now, the key thing now is to make y the subject of the formula. So we swapped our coordinates around. Obviously, a function, we write functions as a function of x, as a function of the x coordinates on the x-axis. That's how it works. So we want to make y the subject of the formula. So now make y, now make y subject of formula. Okay, so we're going to do that now. We're going to make y the subject of the formula. And when we do this, so we're going to get, well, let's just multiply the fractions, both sides of the equation by this denominator. We get x times y plus 4 is equal to 3. So 3 minus 2y. 3 minus 2y. I'm just going to make my writing smaller just to fit everything on the same page. There we go. And then if we just expand the brackets, so we get xy, therefore xy plus 4x equals 3 minus 2y. We want to make y the subject, so let's just try and get the y's on the same side. So we got 4x equals 3 minus 2y minus xy. Take away the 3 from both sides. We get 4x minus 3 equals, so minus 2y minus xy. And if we just factor out a y from the right-hand side, so we get 4x minus 3 equals y times by minus 2 minus x. We can now divide both sides by this factor of minus 2 minus x to get y to be our subject of our formula. So we're going to get, if we do this, we're going to get, so therefore we get y equals 4x minus 3 over minus 2x minus, sorry, minus 2 minus x. It's probably a bit neat. I mean, that's fine, that's acceptable. It's probably a little bit neater just to rewrite this. So if we times every single term, that term, that term, that term, that term by -1, we get exactly the same fraction. So I mean, we could just make every term negative essentially. So minus minus 3 is 3, minus 4x is just minus 4x, minus 2 is 2, and minus x is just plus x. So this fraction here is exactly the same as this one. I've just times the top by -1, times top by -1, and times bottom by -1. I'm just negating all of my terms. So that means that our inverse function, so our inverse function, f inverse, is going to be 3 minus 4x over 2 plus x. So that is going to be our inverse function. Now, obviously, for a function to be defined, as we mentioned before, we need to have a domain of a function. We need to have that domain defined. And yeah, we don't have a domain here. I've not given the domain for this one here. We're going to do that in the next video. So in the next video, we're going to look at finding the domain and range of inverse functions. So this video really is just about how we calculate an inverse function. But in the next video, we're going to look at how we can find the range and domain of inverse functions.